Here we will try to recall how to do the pre-processing of fMRI data, in particular the event-related fMRI experiment, which is well described in the chapter 31 that is called Phase fMRI Data. This is the chapter in the manual for SPM12. Here I list the steps of pre-processing of the data. First, the reorientation of both structural and functional data so that they fit well the canonical template. Then this step is manual. The second one is automatic. Realignment of the functional scans so that all functional scans fit pretty well each other. That corrects for slight motion that can happen during the scanning session. After this, a very special step, Slicetiming correction, which we didn't use for block design experiment. Here, since the events and the responses are very brief, this step can be important, and I will explain why. Afterwards, Coregistration. This time it is an automatic fit of the structural image to the functional images. The next step is segmentation. During segmentation, the segments of the brain tissue, like gray matter, white matter, cerebrospinal fluid, are separated automatically, and the deformation field is estimated. The deformation field is a file where the information about how the individual image must be deformed so that it fits the structure, the shape, and the proportions of the canonical MNI template, so that we can well average inside the group and give to each of the activated areas clear MNI coordinates. So this information will be used during normalization of functional images and normalization of structural image. And after, the last step is the smoothing of the functional images. First of all, we need the data. The data are freely available on the site. This is where it is. Here you can download the manual, which the PDF file which will be used during my presentation, and the data archive. I already downloaded it, and it is located on my disk here in the folder face rep. Now I'm going to unzip the data to the main folder. Takes a few seconds. The browser can be closed. Let's put all the files and folders in the main folder. And delete this one since it is not necessary. This is where all the functional data are located. This is where the structural image is stored. Let us create new folders for functional and structural images so that we don't change anything in the raw data. It is very important for us to always keep the original files. If something goes wrong, we can always go back and redo the analysis. This is structural. And this is functional. The functional data folder has a lot of files, and if you open one of the images, you see that it is functional image, normally much inferior quality and resolution than the structural one. In the structural image, you see that the quality is much better and the resolution is high, but there is only one image. Now let's go to SPM. We can open it in Matlab command window, SPM fMRI. And compare our structural images and functional images. To compare two images, the orientation and position, we use function checkReg. Go to functional and take the first one, and we go to structural and take the first one. Let us see if the orientation of the two correspond well to each other. In order to project the contours of one image into the other, we right-click on the image which we have to project, select Reorient Images, and click on Current Image. As we can see, those two images fit each other very well. But do they fit well the canonical template? This is other question. Now we queue to Reorient Image, Click check right again. And now we compare the structural image, which has much better resolution if you remember, to a canonical template, which is stored in the folder SPM12 canonical. You can pick one of the average T1 or a single subject T1 image. It doesn't really matter. They all work well for this purpose. And then you select the structural image. As you can see, the orientation is not really correct. And we are going to reorient our image toward the template. After we identify the optimal reorientation parameters, we apply them to both our single structural image and all of our functional images. We go to reorient images, select current image, and now we project our individual structural image to the template. So what can be done here? I guess we should move it 10 millimeters up, a little bit backward. We add a negative value to the window for forward displacement. Let's say -10. And now we add some pitch, which is sort of bending the neck forward. +0.1. I think we can add a bit more. +0.2. It is in radians, not in degrees. I think this is enough. We don't have to fit them perfectly well. The purpose is to make our images to be located approximately in the same position and the same orientation. Now we apply those parameters to the images. First, of course, the structural, but also we apply the same reorientation to all the functional images. How many functional images do we have? Let's check it in our manual. So there must be in total 351 functional images, starting from SM039530005. Let's see the image selector if we have the necessary number. Yeah, indeed, it starts. Well, there is no such an image as 005. Perhaps it's an error in the manual. But let's see the total number. We select all, and we have 352, which is correct. We have one structural and 351 functional images. So now we can click Done. Save reorientation matrix. We can save it here in the folder of structural, and this is the name of the matrix. If we want to replicate the reorientation, we can apply the same parameters again. Or we can move backward to the original orientation of the images. And let's check again if the structural and the canonical images fit each other well enough. Yeah, you can see the structure and the orientation is about the same. not the structure, the orientation. The structure is different, of course, because this is the average image collected from many subjects, and this is an individual image, and not normalized at all. So the shape is quite different. But this is going to be corrected at the stage of normalization. Let's check again if the structural image still fits the functional image. Yes, everything is correct. We can check it more carefully. It's always useful to double check your the outcome of your transformation with check range, so that there is no error in your data processing, at least when you do it for the first time. Okay, now we can view to orient. Sorry, you have to click on the image that you project, so that you stop this. And the next step is automatic realignment. This is pretty easy. You click realign, estimate, and reslice. This is where you have to select the data to create first session, and we have only one session, and you select all the functionals. There must be 351 files. And don't forget to save the job or the batch file in a designated folder. There must be folder jobs in your main folder that's created. This is where we are going to store all the files with the tasks we give to SPM for preprocessing. So we click here to save it, go to jobs, and we save it. The file name can be arbitrary, but I like to start the file name from a number, so that you remember not only what has been done, but also the order of those processing steps. And you call it realign. Save. And after you can run. In SPM interactive window, you can see the progress bar. This means that everything is correct. And at the end of the realignment, we will probably see an image like this. Those are calculated parameters of the displacement of the functional images. Here you see the 3 transitions in X, Y, and Z direction, and those are 3 rotations around respective axes. This information will be stored in a separate file. And this file is going to be used for our statistical analysis. This file is located in the folder where all the functional images are located. Also, there will be an average functional image generated at the end of this processing step. And this image will also be used later for coregistration. And the next step is slice timing correction. What is it? Here I have to give you some explanations, and I prepared a small illustration. This is a sagittal view of the functional scan, and with blue and red thick lines I highlight the orientation of the scan. The flat of the slice. The slices are flat, 1 voxel wide, with certain area, and they are acquired in a certain direction. For example, from the top to the bottom. In total, there are 24 slices in one scan, and it takes 2 seconds to acquire the whole image, the whole functional image. So this is the first and this is the last, and the time interval between the first and the last is called TA, which is the time between those set of the first and the last slice, and calculated using this simple formula. You just have to subtract the whole TR, which is the time between the onsets of the first slice of the one volume and the first slice of the next volume, and TR divided by n of the slices. This doesn't mean that in the file the first slice is what it was acquired first. Maybe it is stored in other sequence, and this is known from the technical characteristics of the sequence you are using. In this particular case, the slice acquisition order is inverse. Why do we need to do slice timing correction? Because this delay between the acquisition of the first and the last slice can also postpone the hemodynamic response we want to detect. This is the response to an instantaneous event and at point 0 in the first slice. And this is the response recorded from the last slice. There is a systematic delay, which is a systematic error. If we try to find something like this, we will probably fail to do it effectively in the lower portion of the brain, while it will be well detected in the higher portion of the brain. That is why slice timing correction helps us to correct for this delay by sort of interpolation of the data. And it is pretty easy to do. You just click slice timing, you select all the functional realigned scans. That's why you can use the mask caret R, select all, and there must be as usual 351 file. Let's check what else have to be indicated. So the number of slices must be 24. TR is 2 seconds. between two different scans. TA is 2 minus 2 divided by 24. It will automatically calculate exact value. And slice order is from 24 with a step of -1 to 1. This is classical example of Matlab syntaxes. If you are not familiar, just replicate what is advised. And so you see it is from 24 to 1. And the reference slice is recommended to be 12. We save everything to jobs. Slice timing. And we run it. Here the prefix is A. The prefix for realignment was R. Each time the file is modified substantially, a kind of prefix is added. This helps a lot to identify steps of the processing. And each time a lot of new files will be generated. This is the progress bar. Okay. This part of preprocessing is finished. The next one is coregistration.